We've talked about ionic compounds dissolving, and we learned some solubility rules to help us to determine whether an ionic compound is soluble or not. The process by which an ionic compound dissolves is actually an equilibrium process. And that's why some of the things were soluble and some of the things were slightly soluble. That's a dissolving reaction that only goes a little bit. Some of them go far to the products and some go almost none to the products. So the equilibrium expression for dissolving is called the solubility-product constant. I don't know why. That's what they call it, KSP. SP for solubility product. It's the expression for a chemical equation representing the dissolving of an ionic compound. So just to remember, solids are omitted from equilibrium expressions. If we have a large KSP, that means the reactant, the compound, is very soluble. If we have a small KSP, that means it's not very soluble. When we're writing expressions for KSP, the first thing we have to start with is the equation for the chemical reaction. We want to show the solid compound as the reactant in equilibrium with its dissolved ions. So if we're looking for the expression for the solubility of barium sulfate, I'm going to take barium sulfate solid and I'm going to split it into its ions. It will dissolve into a barium ion and a sulfate ion. So this is my chemical equation, and then I write the equilibrium expression from that. It's the barium ion concentration times the sulfate ion concentration. Normally we would divide it by the reactant concentration, but it's a solid, and we leave solids out because they don't change. So that's the KSP expression for barium sulfate. These numbers have all been determined by experimentation. Question?
The KSP is always going to be solid.
Sorry, I'm lost. Hang on a minute.
It's always going to be...
The reactant is always going to be a solid. Yeah. Because we're talking about it dissolving. Okay, I finally got the same. No? Yes. Sorry. I had different pictures on these screens. It's very confusing to me. The reactant is always going to be a solid, because that's the reaction we're looking at. Okay, you stick a solid in water, and theoretically everything could dissolve, right? You could separate it into ions on paper. The question is, does it really separate into ions in the water? And so when we look at a table of solubility product constants, so here are the formulas, here are the KSPs. Things that have very small numbers like minus 29, lead sulfide, is considered to be insoluble. The truth is, though, a few of the ions will dissolve. It's not that none of it dissolves, it's just that such a tiny percentage dissolves that it doesn't matter. Others of these are higher. None of them are very high, though. Probably the best one on here is calcium sulfate, is at 10 to the minus 5, and lead chloride is 10 to the minus 5. Those are still not very soluble. Let's write expressions for KSP for each of these compounds. We first write a balanced chemical equation for the solid compound separating into its ions. So for this first one, we have AgI solid in equilibrium with its two ions. Well, there's Ag and there's I. And we need to know the charges on those. So this is back to like chapters 4 and 5 stuff. Silver is plus, and that's going to be aqueous. And iodine is minus, and that's going to be aqueous. Then the KSP expression, KSP, is equal to the products times each other and raised to a power of any coefficients that might be there. So silver ion and iodide ion. The reactant is left out because it's solid. Any questions? Let's do calcium hydroxide. So calcium hydroxide, solid, in equilibrium with its ions. So calcium has a 2+ charge. And then we have OH minus, but there's 2 of them because we've got this OH2. So for every one of these, we get 1 calcium and 2 hydroxides. So then KSP equals the calcium ion concentration times the hydroxide ion concentration squared. Questions? When we talk about the solubility of a compound, that's the amount of compound that will dissolve in a particular amount of liquid. We might be interested in how many grams of sodium chloride could dissolve in 1 liter of water. There's lots of different units that we could use. We're going to just look at the molar solubility. The molar solubility is the number of moles of a compound that will dissolve in 1 liter of solvent. So it's how many moles per liter. That's the same unit that's used in equilibrium expressions, so that makes it easy. We can calculate this from KSP. It is sometimes abbreviated with a capital S. So let's do an example. Determine the molar solubility, S, of silver chloride. And we're given the chemical equation showing how it dissolves, and we're given the value of KSP. We want to know how many moles of silver chloride will dissolve per liter of solution. What we're going to do is we're going to write the KSP expression. So KSP equals the silver ion concentration times the chloride ion concentration. And that is equal to 1.77 times 10 to the minus 10. Well, what is S? S, the molar solubility. That's moles of silver chloride per liter that dissolve. If 1 mole of silver chloride dissolves, how many moles of silver ions do I get? 1. How many moles of chloride ions do I get? 1. For every one of these that dissolves, I get 1 of each of these ions, right? If I have a pair of shoes and I separate the shoes, how many left shoes do I have? 1. And how many right shoes? 1. If I have 15 pairs of shoes and I separate them, how many right shoes do I have? 15. They came together. They have to have the same number. Does that make sense? So S is the concentration of silver chloride that will dissolve. The concentration of silver ion is equal to the concentration of chloride ion because they came as pairs. That equals the chloride concentration. And that is equal to the molar solubility of silver chloride. So if I start with 15 moles of this, I'll get 15 moles of that and 15 moles of that. All the numbers are equal. So what I can do is I can put S in for Cl minus, and I can put S in for Ag plus. And then that is S times S. So this is equal to S times S, which is S squared. So S squared equals 1.77 times 10 to the minus 10. Any questions yet? I want to know what S is, so I'm going to square root that side, and I'm going to take the square root of this side. S is the square root of 1.77 times 10 to the minus 10. So I get out my calculator, 1.77 times 10 to the minus 10. .33 times 10 to the minus 5. And the units is moles per liter. Any questions? This can get much more complicated if this isn't a one-to-one stoichiometry. So we're mostly going to avoid that. Okay? Because there's no point. There's no point in torturing you. I think you probably feel tortured enough as it is, right? Calculate the molar solubility of calcium sulfate. There's no numbers in the problem. What do we do? Well, we need a number. We're going to have to look it up. That's why you have a book. Look, there's this nice table. Calcium sulfate, 7.10 times 10 to the minus 5. KSP equals 7.10 times 10 to the minus 5. So I need to write the equilibrium expression. First, I need the chemical equation. So that's calcium sulfate as a solid, and that's going to be in equilibrium with its ions. It's always two ions. There's calcium, that's aqueous, and there's sulfate. There's just one of each. So then the KSP expression, KSP equals calcium times sulfate. And that equals 7.10 times 10 to the minus 5. Oh, that's not very pretty. So let me describe the use of S a little bit differently. Let S equal the moles of calcium sulfate that dissolve per liter. So the moles that dissolve over the liters of solution. Pardon my sniffing. Looking at this chemical equation, for every 1 mole of this that dissolves, we get 1 mole of calcium. For every 1 mole of this that dissolves, we get 1 mole of sulfate. So S then is equal to the calcium concentration. S is equal to the sulfate concentration. S equals the calcium ion concentration, and it equals the sulfate ion concentration. So then I can say that this is equal to S squared. So S equals the square root of the KSP. So that's the square root of 7.10 times 10 to the minus 5. 7.10 EE minus 5. 8.43 times 10 to the minus 3. I know that's an ugly 3. I don't care. Any questions?